The paper presents a comprehensive analysis of the random batch method with replacement, RBM-r, for simulating interacting particle systems. RBM-r is an efficient algorithm that reduces the computational cost from O(n²) to O(p)n) per time step, where p represents the batch size. The algorithm randomly picks a small batch of size p, and only the particles in the picked batch interact among each other within the batch for a short time, with the weak interaction replaced by a strong interaction. The authors provide a rigorous proof of the convergence of RBM-r with an explicit convergence rate. They also obtain an improved rate when there is no diffusion in the system. The techniques used in the analysis can potentially be applied to study kinetic Monte Carlo (KMC) methods for other systems, including the stochastic Ising spin system. The interacting particle system is modeled by a first-order pairwise interacting particle system in Rho, described by a stochastic differential equation (SDE) system in Ito's sense. The system consists of n indistinguishable particles, each interacting with each other according to some interaction force. The interaction force is a weak interaction, usually of strength 1, n, which requires O(n²) complexity per time step. The authors discuss the applicability of RBM to other systems, including non-binary interacting particle systems, systems with unequal weights, charges, or volatility, and systems with degenerate or multiplicative noise. They further mention that RBM can be extended to jumping processes like the stochastic Ising model. In addition, the paper reviews the random batch method, RBM, as a novel algorithm for simulating interacting particle systems, which significantly reduces computational complexity to O(n)(t)(n). It has been applied to various practical algorithms, such as the random batch yield method for molecular dynamics, sampling, interacting quantum particle systems, second-order interacting particle systems, multi-species stochastic interacting particle systems, the Poisson-Nernst-Planck equation, and the homogeneous Landau equation. Both RBM1 and RBM-r share similar implementation details, convergence properties, and computational complexity. RBM1 converges to the original interacting particle system as kappa right pointing arrow 0, with a convergence rate under Wasserstein 2 distance of O, square root kappa plus kappa squared. RBM-r also converges to the original interacting particle system at time t, with an explicit convergence rate. The geometric ergodicity of RBM dynamics and some convergence of numerical discretization for RBM of dynamics have been well studied via specific coupling methods. A sharp error bound for the numerical discretization of RBM has been established, motivated by advanced techniques in data science and machine learning communities. The mean field limit, the n-right pointing arrow infinity region, of the random batch method has also been studied in recent years. The authors establish the convergence of the random batch method with replacement, RBM-r, algorithm to interacting particle systems, IPS, in Wasserstein 2 distance, under certain conditions on the potential function V and interaction kernel K. The main result, stated in Theorem 2.1, bounds the Wasserstein 2 distance between the first marginal distributions of the IPS and RBM-r by C kappa caret 1/4. Where C is a constant depending on the system parameters and kappa is the time step. The proof relies on a novel coupling method, introducing an intermediate dynamics IPS, with n copies of the IPS after random time change. The authors utilize the diagonal principle during the analysis, coupling the Brownian motions in a specific way to facilitate the proof. The key insight is to synchronize the paired dynamics, x, using the same Brownian motion, allowing for the derivation of a bound on the Wasserstein 2 distance. The RBM-r algorithm is a discretization of the IPS, where at each time step, a random batch of particles is chosen, and the interaction force is calculated based on this batch. The authors construct a coupling between the IPS and RBM-r, using the random time change relation induced by each index I to estimate the distance between the IPS and RBM-r. The authors propose a two-step approach to estimate the distance between the IPS and RBM-r, using the Holder's continuity property, the law of large numbers, and the Lipschitz assumption for the interaction kernel K under the assumptions of strong convexity and polynomial growth of the potential function V, and boundedness and Lipschitz continuity of the interaction kernel K. The authors proved that the Wasserstein-2 distance between the first marginal distributions of the IPS and RBM-r converges to zero with an explicit rate, specifically O, kappa caret 1/4. The paper analyzes the convergence rate of the random batch method with replacement, RBM-r, to the interacting particle system, IPS, in a mean-field limit. It is shown that RBM-r converges to IPS as the number of particles n and the batch size p tend to infinity, with a convergence rate of O, kappa caret 1/4, which can be improved to O, kappa caret 1/2, when there is no diffusion, i.e., sigma equals 0. To prove the main result, the authors introduce an intermediate dynamics, IPS, which consists of n copies of IPS after a random time change. They define a triple of dynamics, x, 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 with the same initial state, and couple the Brownian motions to establish a synchronous coupling between RBM-r and IPS. This allows for the estimation of W2, ρ, 1, npt, ρ, 1, t, the Wasserstein-2 distance between the first marginal distributions at time t for RBM-r and IPS. The proof involves applying the law of large numbers and the H-diaresis-Older's continuity property of the SDEs, which are essential for establishing the convergence rate. The authors then compare RBM-r with IPS, and IPS, with IPS, using a random time change relation to construct a suitable coupling. This leads to an O, square root kappa, upper bound for the distance between IPS and IPS. By decomposing the process Z into three parts, the authors estimate the distance between IPS and RBM-r, resulting in an O, 1, square root n, upper bound. Combining these results, they obtain an O, square root kappa plus 1, square root n, upper bound for the distance between RBM-r and IPS, indicating that RBM-r approximates IPS well when both the time step size kappa and the number of particles n are large enough. The paper also discusses the limitations and assumptions of the analysis, as well as potential future work directions. The authors delve into the dynamics of the system, focusing on the first, second, and third terms of the dynamics equation, utilizing strong convexity, Lipschitz conditions, and the law of large numbers to estimate these terms. Specifically, they demonstrate that the first term can be bounded using strong convexity, while the second term is estimated using the Lipschitz condition and exchangeability of the system. The third term is decomposed into three parts, which are then bounded using the consistency of the random batch and the Lipschitz assumption of the interaction kernel. The authors establish several lemmas, including lemma 3.1, which provides uniform and time moment control for the stochastic dynamics, and lemma 3.2, which demonstrates the Holder's continuity property of differential equations. These lemmas are applied to derive an upper bound for the expected squared difference between the interacting particle system and the random batch method, utilizing Gronwall's inequality. Furthermore, the authors discuss the exchangeability of the system, Z, Ni equals 1, defined in RBM-r and IPS, and provide upper bounds for the second term on the right-hand side of equation 2.13, in step 3 of the main proof. They also present a law of large number, as shown in lemma 3.3, which is used during step 2 of the main proof. Additionally, they demonstrate a significant finding in equation 3.5, where they prove that for fixed t greater than 0, for small kappa, and t is less than or equal to t, they have a specific upper bound for the integral of the expected value of the squared difference between xj, js and xj, as over the interval 0, npt. The authors utilize various mathematical tools, including Ito's calculation, Young's inequality, and the law of large numbers, to establish a rigorous and technical analysis of the dynamics of the system. They provide detailed proofs for several lemmas in the appendix, supporting the main proof. The paper delves into the analysis of the random batch method, RBM, for optimizing non-convex functions, a crucial component in various machine learning algorithms. It focuses on the stochastic gradient descent method with random batch sampling, aiming to provide a theoretical understanding of its convergence properties. The authors introduce a new framework that combines the stochastic gradient descent method with the random batch sampling technique, providing a unified analysis for both convex and non-convex functions. They establish an upper bound for the error term, which is a critical component in understanding the convergence rate of RBM. The authors utilize a series of lemmas that control the error brought by the random batch. These lemmas are based on the consistency of the random batch, the Lipschitz and boundedness assumption for K, and the continuity property of differential equations. The lemmas provide upper bounds for the third term on the right-hand side of equation 2.13, which is crucial in the overall analysis. The paper also discusses the time evolution of Xi, I element of Ck, in RBM-r, as given in equation 2.3, for S element of Tk plus 1. By taking the conditional expectation and utilizing the properties of nabla V and K, the authors derive an estimate for E, increment Xi, Fk, as shown in equation 3.17. This estimate is essential in controlling the error term in the analysis. Furthermore, the authors use the uniform moment bound for Xi, as stated in lemma 3.1, and the continuity property of differential equations, as stated in lemma 3.2, to obtain the desired upper bound for the error term. This upper bound is given in equation 3.11, which is a key result in the paper. The paper concludes that the error term in the RBM can be controlled by a function of the batch size and the step size, providing insights into the convergence properties of RBM. This theoretical analysis contributes to a deeper understanding of the stochastic gradient descent method with random batch sampling, shedding light on its applicability and efficiency in optimizing non-convex functions. In the final sections, the authors summarize the main results, discuss potential extensions, and provide proofs for lemmas in section 3. They prove the convergence of the random batch method with replacement, RBM-r, for interacting particle systems, which is equivalent to the kinetic Monte Carlo, KMC, for pairwise interacting particle systems. The authors demonstrate that RBM1 converges to the associated interacting particle system under Wasserstein 2 distance with an explicit rate, which can be improved when there is no diffusion in the system. The authors suggest that a natural extension of their method is to study the kinetic Monte Carlo applied to other dynamics, such as the stochastic Ising spin system. They propose using their method based on random time change and the law of large numbers to provide a rigorous proof of KMC for suitable models. Another potential direction for future work is to develop advanced analysis tools to improve the current convergence rate from O, kappa caret 1/4, to O, kappa caret 1/2, even when the volatility sigma is non-zero. In the appendix, the authors provide detailed proofs for lemmas 3.1, 3.2, 3.3, and equation 3.9. Specifically, they estimate the process Xi, T, using Ito's formula and lambda convexity of V, in assumption 2.1. By applying Young's inequality and choosing small nu and nu, they obtain a bound for the second term on the right-hand side of equation, A.1. This leads to a moment control for Xi, T, in equation, A.2. The authors also estimate the process Xi, T, using the random time change relation and the boundedness of K, from assumption 2.1. They apply Gronwall's inequality to obtain a bound for Xi, T, in equation, A.3. Similarly, they estimate the process Xi, T, and apply Gronwall's inequality to obtain a bound in equation, A.5. Overall, the authors provide a rigorous analysis of the random batch method with replacement and its application to interacting particle systems, highlighting potential extensions and areas for future work. The authors derive bounds on the expectations of the squared differences between the processes XL, I, XL, X, and Z at different time points. For XL, I, the expectation of the squared difference between XL, I, T2, and XL, I, T1, is bounded by C, T2 T1, 2 plus 3 sigma 2, T2 T1, where C is a positive constant independent of I, L, K, T1, T2, N, P, and sigma. Similarly, for XL, the expectation of the squared difference between XL, T2, and XL, T1, is bounded by C, T2 T1, 2 plus 3 sigma 2, T2 T1, where C is a positive constant independent of L, K, T1, T2, N, P, and sigma. For X, the expectation of the squared difference between Xi, T2, and Xi, T1, is bounded by C, T2 T1, 2 plus 3 sigma 2, T2 T1, where C is a positive constant independent of I, K, T1, T2, N, P, and sigma. Lastly, for Z, the expectation of the squared difference between Z, T2, and Z, T1, is bounded by C, T2 T1, 2, where C is a positive constant independent of I, L, K, T1, T2, N, P, and sigma. The authors also introduce the sequence tau k, k, which is I, D, and geometrically distributed with expectation E tau ik equals n, p, and variance var tau ik equals n2, p2n, p. This result is used to establish an upper bound on the expectation of the squared difference between kate int and npt. Furthermore, the authors derive an upper bound for the integral of the squared difference between two random variables, tau I nis and tau j njs, where nis and njs are binomially distributed random variables representing the number of times particles with indices I and j are chosen into a batch before time grid tk. The bound is expressed in terms of the variance of nis and njs, which are shown to be k plus 1 p underscore n, 1 p underscore n, where p underscore n is a parameter. The authors use the Tower property and the mean and variance of tau I nis and tau j njs to rewrite the integral as a sum of three terms. The first two terms are bounded using the mean and variance of nis and njs, while the third term is bounded using the variance of nis and njs. The final bound is expressed in terms of the parameters n, p underscore n, and kappa. The authors also provide a list of references, including papers on binary interaction algorithms, characterization of radially symmetric finite-time blowup, scaling theory for metastable states, plasma physics via computer simulation, and kinetic limits for pair interaction-driven master equations, among others. In summary, the authors derive bounds on the expectations of the squared differences between various processes at different time points, introduce a geometrically distributed sequence, and establish an upper bound for the integral of the squared difference between two random variables. These results are used to analyze the behavior of particle-based models of swarming with uncertainty. The random batch method, RBM, is a stochastic approximation technique that has been successfully applied to various fields, including interacting particle systems, quantum Monte Carlo simulations, and molecular dynamics. It efficiently estimates the mean field limit for large interacting particle systems with Coulomb interactions, making it suitable for complex systems where traditional methods are computationally expensive or intractable. The paper delves into the convergence properties of the RBM, providing error estimates and discussing the propagation of chaos. For second-order interacting particle systems, the RBM demonstrates near-optimal rates without convexity. In quantum Monte Carlo simulations, the RBM solves integral equations of classical potential theory rapidly. In molecular dynamics, the RBM improves the Ewald method, leading to superscalability in simulations. However, the paper also addresses the limitations and assumptions of the RBM, identifying areas for future work. The RBM is presented as a versatile tool for solving complex problems across multiple domains. The authors emphasize the need for further research to fully exploit the capabilities of the RBM and explore its applications in other domains.